Welcome to Get Your FRQ On. This question is from 2010. It's question 5, and it is not calculator active. In the question stem, we're given a function g which is defined and differentiable on the closed interval from -7 to 5. We're also given that g of 0 is equal to 5, and we're provided with a graph of g prime of x. In question A, we are asked to find g of 3 and g of -2. All right, so this is pretty much a straightforward fundamental theorem of calculus problem. The integral from a to b of f prime of x dx is f of b minus f of a. So we can find g of 3 by thinking of the integral from 0 to 3 of g prime of x dx, and then just adding g of 0 onto that. So g of 3 is g of 0 plus the integral from 0 to 3 of g prime of x dx, which, using the graph and some area calculations from geometry, we're going to get 5 plus 1.5 plus pi, and so g of 3 is the sum of all that, which is 6.5 plus pi. G of -2 can be found similarly. This is just going to be g of 0 plus the integral from 0 to -2 of g prime of x dx, which is the same as g of 0 minus the integral from -2 to 0 of g prime of x dx, which, doing more area calculations, is 5 minus pi. In part B, we are asked to find the x-coordinate for each inflection point of g on the open interval from -7 to 5 and explain how we know that it is in fact an inflection point. Right, so the function g will have an inflection point at any x value for which g prime of x changes between increasing and decreasing in either order. It doesn't have to be increasing to decreasing, it just has to change between them. So look at the graph of g prime of x that's provided. When does it change between increasing and decreasing? Well, the graph of g prime of x changes from increasing to decreasing at x equals 0. It changes from decreasing to increasing at x equals 2. And it changes from increasing to decreasing at x equals 3. So the x-coordinates for the inflection points are 0, 2, and 3. In part C, we define a new function h of x to equal g of x minus 1/2 of x squared, and we are asked to find critical points of h on the open interval from -7 to 5, and then to classify them as either maximums, minimums, or neither. All right, so critical points of h will occur whenever h prime of x is equal to 0 or h prime of x is undefined. Right, well, h prime of x is going to be g prime of x minus the derivative of 1/2 x squared, which happens to just be x. Right, so we're given that g of x is differentiable, so we don't have to worry about g of x or g prime of x being undefined somewhere. And 1/2 x squared is a polynomial, so that's differentiable for all real numbers. Don't have to worry about that. You should state it, though. You do want to make sure that you verify that you can conclude that h of x is differentiable everywhere, which is the goal. So if h of x is g of x minus 1/2 x squared, h has to be differentiable for that entire interval as well. All right, so differentiating h of x, we get h prime of x equals 0, implies that g prime of x minus x equals 0, or g prime of x equals x. So here's what we do with that information. We need to know when g prime of x is equal to x. In other words, are there any points on the graph of g prime of x where the x and y coordinates are the same? In other words, the line y equals x, does that ever intersect the graph of g prime of x? Well, it does. Right, based on the graph of g prime of x provided, g prime of x will equal x whenever x is equal to the square root of 2 or just 3. All right, so how do we classify these? Well, the derivative of g is less than the value of x when x is between the square root of 2 and positive 2. right? This implies that h prime of x is less than 0 for that interval. G prime of x is greater than x for x between 0 and square root of 2. This implies that h prime of x is greater than 0 for x between 0 and square root of 2. And g prime of x is less than x for x between 2 and 4, which implies that h prime of x is less than 0 for x between 2 and 4. So, from this analysis, we conclude that h of x has a relative maximum at x equals 2, and neither of these, neither a maximum nor a minimum at x equals 3.